Every month, in most households across the United States, a number arrives. It appears in a paper statement, or in an email, or inside a utility app notification. The number represents the total cost of electricity consumed during the previous billing cycle, typically between 28 and 32 days. Most household members look at that number. Some compare it to the previous month. A smaller number compare it to the same month in the prior year. And then, in most cases, the bill is paid. What most households do not do, and what most billing systems do not facilitate, is trace that number backward to the specific appliances that produced it, backward to the specific hours during which those appliances were running, backward to the specific rate that was applied to each kilowatt-hour consumed. The number arrives as a single undifferentiated total, and the behaviors that produced it are already 30 days in the past. Research conducted by the Lawrence Berkeley National Laboratory and replicated in subsequent studies by university energy behavior departments has consistently identified a specific and measurable gap between what households believe they consume and what metering data shows they actually consume. The gap is not small. In study after study, residential participants underestimate the energy consumed by their largest draws: heating systems, cooling systems, water heaters, and refrigeration, while simultaneously overestimating the impact of their most visible behaviors: turning off lights, unplugging phone chargers, reducing television use. The behaviors that households manage most actively are, in most cases, the behaviors that matter least. The systems that account for the majority of consumption run continuously, quietly, and largely outside the household's field of attention. This is not a new observation. Utility companies have been aware of this perception gap for decades, and a number of tools have been developed in response. Online usage portals, now standard across most major utility providers, allow customers to view historical consumption data, broken down by day and, in some cases, by hour. Time-of-use pricing programs, available in certain utility territories, are designed to create a price signal that makes high consumption periods financially visible to the customer. In-home display devices, small screens installed near the electrical panel or in a central household location, show real-time consumption in kilowatts and, in some versions, in dollars per hour. Smart thermostats, now widely available at consumer retail price points, collect and report heating and cooling runtime data and provide monthly energy summaries. Each of these tools addresses part of the problem. None of them closes the gap entirely. The usage portal shows historical data, but historical data describes what already happened. It does not show, at the moment a decision is being made, what that decision will cost. Time-of-use pricing creates a financial signal, but interpreting that signal requires the household member to know which appliances draw the most power and to adjust behavior accordingly in real time across multiple systems simultaneously. The in-home display shows real-time consumption, but the number it displays is aggregate. It shows total household draw at that moment. It does not attribute consumption to individual appliances or circuits. The smart thermostat reports on one system. It does not report on the refrigerator, the water heater, the dryer, the dishwasher, or any other load running at the same time. The tools exist. The data they provide is real. The gap persists anyway. Understanding why the gap persists requires examining the design of the system that produces the billing number in the first place. The residential electricity meter, in most U.S. households, still a mechanical or basic digital device located on the exterior of the structure, measures one thing: total cumulative energy consumed since the last reading. It does not measure which appliances drew that energy. It does not measure when, during the billing period, the heaviest consumption occurred. It does not distinguish between a household that ran its air conditioning continuously for 30 days and a household that ran it intermittently. If both households consumed the same total kilowatt hours, the meter produces the same number. The billing statement compounds this limitation. A standard residential electricity bill contains multiple line items: base customer charges, distribution fees, transmission charges, fuel adjustment clauses, and various regulatory surcharges, each calculated differently, each present regardless of how much electricity the household consumed. The base customer charge, for example, is a fixed fee assessed simply for being connected to the grid. It does not vary with usage. A household that consumed 200 kilowatt hours and a household that consumed 2,000 kilowatt hours in the same billing period pay the same base customer charge. In most utility territories, this fixed cost layer represents between 30 and 50% of a typical residential bill. This means that even a household with accurate, detailed knowledge of its own consumption and with the behavioral discipline to reduce that consumption significantly, it cannot reduce its bill proportionally. A 40% reduction in kilowatt hours consumed does not produce a 40% reduction in the bill. It produces a reduction applied only to the variable portion of the charge. The meter continues to run. The fixed charges continue to accumulate. The household's ability to observe the relationship between its behavior and its cost is structurally constrained, not by a failure of attention, but by a failure of design. The system was not built to provide that feedback. It was built to aggregate consumption across a billing cycle and produce a total. That is what it does. The consequence of this design is not simply that households pay more than they expect to. The consequence is that the feedback loop required to change behavior does not exist at the point where behavior occurs. A household member standing in front of an open refrigerator, deciding whether to leave the door open for another 10 seconds, has no information about what that decision costs. A household member running the dishwasher at 7 p.m. during a period of peak grid demand and elevated pricing has no indication that the timing of that decision affects the rate applied to the energy it consumes. A household member who keeps the thermostat at 72 degrees throughout a week-long heat event has no real-time visibility into what that single week will contribute to the total that arrives at the end of the month. The decisions happen continuously. The feedback arrives once, aggregated 30 days later. The design constraints described here apply specifically to the standard residential utility model, the model under which the vast majority of U.S. households currently operate. They do not apply universally. Alternative configurations exist in which the feedback loop is structured differently. In households that generate their own electricity through solar installations, backup generation systems, or other means, the relationship between consumption and cost is, by definition, different. The household is not receiving a bill calculated by an external party using rates it did not set. It is consuming energy it produced from a system it owns, with costs that were determined at the time of installation rather than at the time of use. In these configurations, the household has direct visibility into generation and consumption in a way that the standard utility model does not provide. The monitoring systems associated with residential generation whether solar inverter dashboards, battery management interfaces, or generation monitoring devices, are typically designed to show real-time output and consumption simultaneously. The household can observe at any moment how much energy is being produced and how much is being consumed. This does not mean that alternative configurations are without complexity. Solar installations carry significant upfront cost, require structural assessment of the property, involve permitting and interconnection processes with the utility, and perform variably depending on geographic location, roof orientation, and seasonal conditions. Other generation formats carry their own constraints: fuel requirements, maintenance schedules, noise, emissions, and portability limitations. The point is not that alternatives are superior. The point is that the feedback gap, the structural absence of real-time consumption visibility, is a feature of the standard utility model specifically. It is not an inherent property of electricity as a resource. Within the category of alternative generation formats, a subset of systems has received increasing attention from households, specifically because of their relationship to the feedback problem described here. Small-scale, self-contained generation devices, systems that operate independently of the utility grid and do not require interconnection agreements, permitting processes, or large capital expenditure, represent one end of the spectrum of alternatives available to residential consumers. One such product currently in distribution is the Space Energy Generator, a guide and blueprint system that provides instructions for constructing a small-scale mechanical generation device from components available at standard retail hardware and electronic suppliers. The product does not require a licensed electrician for installation. It does not require a utility interconnection agreement. It does not involve a roof installation or weather-dependent generation conditions. The relevance of this format to the structural problem described here is specific and limited. A household using a self-contained generation device to power a subset of its appliances or its entire load, depending on system scale, is no longer dependent on the utility billing cycle for visibility into what those appliances cost to run. The cost of the system was determined at the time of construction. The consumption of energy from that system does not generate an external bill. The feedback loop, while still imperfect, is structurally different from the one produced by the standard utility model. Whether that difference is meaningful for any specific household depends on variables this video cannot assess: the household's load, its physical location, its regulatory environment, its capital availability, and its tolerance for construction and maintenance tasks. The product exists. Its relevance to the problem described here is structural, not promotional. What it represents, in the context of this video, is one data point in a broader category of systems that address the feedback gap from the generation side rather than the metering side. The gap between what households believe they consume and what they actually consume is documented, consistent, and structurally produced. It is not the result of inattention. It is the result of a billing and metering design that was built to aggregate, not to inform. The tools developed to address this gap, usage portals, time of use pricing, in-home displays, and smart thermostats, each address part of the problem. None of them closes it entirely, because none of them can retroactively attach a cost to a behavior at the moment that behavior occurs. The fixed cost layer embedded in most residential bills ensures that even accurate consumption knowledge applied with consistent behavioral discipline cannot produce proportional bill reductions. And the monthly billing cycle ensures that the feedback, when it does arrive, is too distant from the behaviors that produced it to function as an effective corrective signal. These are not temporary conditions. They are structural features of the standard residential utility model as it currently exists. Households that operate within that model operate within those constraints, regardless of how carefully they monitor their usage, how aggressively they manage their consumption, or how many efficiency tools they deploy. The constraints do not respond to effort, they respond to structure.